Okay, yeah, very good.
In this case, to require that we have
Yeah, because in that case, oh, sorry. I thought I had removed. Okay. Ah. So in that case, yeah, that's the point. So you said in that case, which will be the chirality of the largest chirality of the electron antineutrino? Electron antineutrino is mostly right-handed. But this process with electrons on the other side, you need a left-handed particle. Okay? So then this didn't work with reactor antineutrinos because they are mostly right-handed. But if you remember, I also said that due to the mixing, due to that they are massive states, there is a mixing between left-handed and right-handed states. And then even the antineutrino, even if it is mostly right-handed, it has a small component left-handed. Why why with this small component is not enough to do the process? You remember when I put this, yeah, maybe I was too fast. When I put this table, I was explaining that in the case of antineutrino, it has mostly it was right-handed, but it has a small component with wrong helicity. And this small component was proportional to the mass of the neutrino over the energy squared. Okay. And then you have to think that the mass of the neutrino is below electron volt, but the energy reactor solar is several MeV. So it is a quite a strong suppression. So even if in principle there should be a small component with the wrong helicity that in principle could be able to work this process, it cannot because of this component is very suppressed. So this is for the first part of the question. But now, does it mean that neutrino is different from antineutrino and therefore neutrino is a particle of Dirac type? What do you think? Any? Okay, so this is the first part of the question, as your colleague just replied, that weak interactions are sensitive to chirality. Then only left-handed neutrinos can produce the process. But as reactor will be mainly right-handed, and with this wrong helicity component very small. But then concerning the other question, but this does not mean that neutrino is a Dirac particle, because a nu E will be like the left-handed projection of the neutrino, and the anti-nu E will be the right-handed projection of the neutrino. So I mean, this does not depend on the neutrino is equal to anti-neutrino. It's just the projection. They are different projections. Okay. And indeed, I mean, with this kind of process, we cannot say anything about the nature of neutrinos. Just as I said this morning, just studying processes with violation of lepton number that will take place only in case of Majorana neutrinos, one can really distinguish between the nature of Dirac and Majorana. Okay. I think it is all. Yeah. So it is everything clear? Yeah, so this is why the idea of Davis was just following the same idea of Reines and Cowan, just to detect reactor antineutrinos. Then once he realized that it could not work, then he focused on solar neutrinos, and at the end it was a very good idea. Okay, any comment on that? Yeah, José Manuel. Yeah. Yes, yes. But the thing is that you need also by weak interaction cannot happen because you don't have the component of the chirality. So, I mean, cannot happen because of chirality, yeah. Yeah, because in the Majorana it will be the same case. You will have different projection of the same field. And then the projection you have is the right-handed doesn't work for this process. Yes. Yeah. Okay, so then maybe we will finish very soon. Then I wanted to ask you something related to the Minimalism model. You remember we have discussed several ways to generate neutrino masses. And one of the most simple and successful is the Minimalism model, where one can explain the light neutrino mass by introducing a very heavy right-handed neutrino, very heavy right-handed in general, several. So here I would like you to ask to estimate the required Majorana masses to obtain light neutrino masses. We know the order of magnitude of light neutrino masses. So then I wanted you to estimate which is the value of the Majorana mass that we need in order to reproduce this mass according to the bounds from cosmology and from neutrino oscillations. And to do that, I want that you assume just one neutrino, just one family, okay? And to consider that the Dirac mass that also enters in the Minimalism model is of the order of the electroweak scale. Sorry, I had changed that, but not in that slide. I'm sorry, because this was a mistake. Yeah. So this is a typo. So I consider the Dirac masses of the electroweak scale. Okay, I write it here. I forgot to correct that one. So MD of the order of electroweak scale. I think it's more clear like that. This means Yukawa of order 1. Okay. So then please, if you can do an estimate of which is the scale of the masses of the heavy neutrinos we need in order to reproduce the current bounds on the scale of the light neutrinos. So you have already they have already the slides, Jose Manuel? Yeah, from this morning. So you have in the website. So maybe you want to check. Already there. So I don't know how you did in the other courses. Maybe somebody wants to do the solution in the Blackboard, or how do you do for the other lectures? There is no common procedure. Yes. Yeah. Maybe you can do this, and then you can ask. I mean, it is quite fast to do it. I didn't want to put some very complicated. So meanwhile, I will correct this. If I just disconnect a little bit, this, then I connect it. There will be no problem, right? Okay. So again, it gets blocked. Okay, now it appears. Now it appears.
Whatever you need.
Okay, now it seems it takes some time to recover the mouse back. No, no, it's okay.
Oh, you're good?
Yeah. But now I need to share again. Okay.
No, you're sharing. You haven't stopped sharing.
Okay.
Mhm.
So I need to
Yep.
ocultar controles and this.
Yep.
Okay, thank you. almost everybody arrives to the number. Is there anybody who needs some help or what's a question? So at the end, you have the formula in the slide. So if you remember for the minimal seesaw model, so we have seen that this should be the Lagrangian with the two components, the Dirac and Majorana. Then after the diagonalization, one gets the mass for the light state, M1, and the mass for the heavy one that is almost MR. So of course, remember that these are the values of the diagonalization, assuming that MR is larger than M Dirac. Okay. You can also do, I haven't thought to put this as an exercise because it's quite simple. You can do the diagonalization of the matrix and just find the two eigenstates and see that this is in the limit of M Dirac smaller than MR. These are the eigenvalues. Okay, so the thing is that if you consider for M Dirac the order of electroweak scale, so around 100 GeV, so you can put 200, but 100 is okay. So I'm interested mostly in the order of magnitude. So for the neutrino mass, I mean, here I was quite generous, but in principle, you can take from 0.1 to 1 electron volt. Now cosmology starts to pushing below, but yeah, I think 0.1 to 1 is enough. So then you just do the simple calculation and you will get that this mass for the right-handed state should be of order 10 to 14 GeV. Okay, so this one needs a very large, very heavy state in order to reproduce the smallness of neutrino mass. Okay, and as I was telling you, even if the model, of course, is very popular and very interesting, very nice, because it's elegant the way that you get the smaller masses for the light neutrinos, but it's hard to have this model where you cannot test, you cannot find this prediction. Yeah. Yeah, yeah, it's not possible to observe because no. But usually, I don't know very well this model you said, but usually the mixing of the particles and the connection is very suppressed due to this mass. Yeah. So the mass results that it basically does not intervene in any of the processes you can. There's no way. And the thing is that, yeah, it goes together with the model. You get this prediction for leptogenesis, but also there, you cannot be, even if you cannot be sure that this is the process that behind the baryon asymmetry of the universe. So this is why people is trying to find different models that with more testable predictions. Okay. So any question about this? Okay, so now related to the neutrino mixing, I wanted you to think a little bit. I derived it a bit fast. The number of parameters one needs to describe the neutrino mixing matrix. And I want you to really understand where all these parameters come from. So the question will be how many angles and phases, the phases could be Dirac or Majorana, we need to describe a unitary neutrino mixing matrix of dimension n. Okay, this I gave you already the results, but you can try to understand why these angles, why these phases. And do the particular case for n equal to 3. And going a bit beyond the second part of the question, I wanted to mention, I don't know if tomorrow I will have some time to discuss a little bit on that, because some models of neutrino masses, as we have seen, the seesaw models, introduce new fermionic states that naturally mix with the light neutrinos. So at the end, we end up with a system, with a matrix, with all the states mixing together, not only the light, but also the heavy, the fermionic heavy states, or neutron heavy leptons. So we have a dimension n matrix, okay, with all the mixing between the light and the heavy sector. But since we are sensitive, our experiments are only sensitive to the lighter part of the matrix, to the mixings between the light neutrino eigenstates. So at the end, the full matrix of dimension n is unitary, and then as a result, the 3×3 matrix in general will not be unitary because it's like a part of a unitary matrix. So I wanted you to think, in that case, if we consider a 3×3 neutrino matrix, mixing matrix, that is not unitary, how many parameters do we need to describe this matrix? So I'm asking how many extra parameters. So besides the parameters we need to describe in the unitary case, if now we consider that the 3×3 matrix is not unitary, how many extra parameters do we need? Okay, it is clear? Okay, so I think you can do the same, just working in groups or. Some of you have already obtained the results. So then my goal here was just to look carefully to the slide we have seen before with the different parameters, just to understand where all these parameters come from. So for instance, concerning the unitary mixing matrix, so if we consider a dimension n complex matrix, in principle, one has 2n² real parameters. But if it is unitary, then we will have n² unitarity conditions. So then we can remove n² parameters. So we will end up with n² real parameters. Okay. Now, if we divide the different parameters between mixing angles and phases, so we can see how many of each there are. So for the mixing angles, one needs to think that these are angles mixing, let's say, different two elements of the all available elements mixes the elements 2 by 2. So we have, for instance, in the 3 neutrino matrix, we have θ1, 2, θ1, 3, and θ2, 3. So this will be equivalent to these combinatories of n elements taking 2 by 2. So then if you do this calculation, then you will have n times n minus 1 over 2. This will be the number of mixing angles. Then, of course, the phases will be the remaining ones. So if we have n squared, we remove the mixing angles, and all the rest will be phases. And then we have seen how one can remove from Dirac. We saw that due to this invariance of the Lagrangian under global phase transformations, then one can subtract 2n minus 1 phases. So at the end, this will be the number of phases observables in the case of Dirac. For Majorana, we have seen that there is not such a freedom to do the removal of the phases because the mass term involving neutrinos is not invariant under global phase transformations. So we can only rephase the fields of the charged leptons. So in that case, one can only remove n phases. And then we will have in total n times n minus 1 over 2 phases. So taking everything together, from these complete phases, n minus 1 over 2, we have seen that this value, n minus 1, n minus 2 over 2, will be Dirac phases, the one we have seen before, while the remaining ones, n minus 1, will be Majorana. Okay, this is what we have seen this morning. So just doing the particular case of n equal to 3, so we will have 3 mixing angles and 3 phases, 1 Dirac plus 2 Majorana. So this is clear to everybody? So then for the second part of the question, the thing is that now we have a 3 by 3 matrix, but it is non-unitary. And the key point is that before, you remember, we had 2n² real parameters, but we were removing n² due to the unitarity conditions. Now we cannot do this step. So at the end, we will have n² more parameters that in the case of a unitary 3 by 3 matrix. So we will have 9 more parameters that in the unitary case. Okay? And there are several ways to parameterize the non-diagonal, the non-unitary, 3 by 3 matrix, but one that I find it is very convenient and interesting, and I'm using to get constraints on the non-unitarity of the mixing matrix from neutrino data is the one here. And the 9 parameters, the 9 extra parameters that one should add, here we are including, we have these 6 alpha coefficients, the diagonals, alpha 1, 1, 2, 2, and 3, 3 are real, so 3 here, while the non-diagonal are complex. So we have the moduli and the phases, so 9. And this is how we get the 9 extra parameters, because here, I mean, this is the parameterization of the non-unitary matrix that takes the original PMNS with all the parameters we have seen before, and this extra factor. And as I said, this is convenient because you can analyze data and comparing with the PMNS elements that everybody knows, and everybody knows the values, and this is why it is convenient. Okay? So it is clear to everybody? If not, please let me know. So just to conclude, I wanted to show you like a practical exercise that for sure there will be no time for you to do in your computer, but maybe if you are interested, you can do it at some point. And it was just to trying to show you how we people that we are doing analysis of neutrino data experiments, we get constraints, we translate the experimental information into constraints in the parameter space of neutrino oscillations. So, for instance, here I'm going to consider the most simple case, that is two neutrino approach and in vacuum. This is the formula we have seen this morning, the two neutrino oscillation formula in vacuum. And then the thing is that one can do some experimental measurement trying to find out the value for this oscillation probability from a given experiment, okay? And then one can have, of course, two different types of results, negative result or positive result. In a negative result would be a result that where the oscillation is not measured. One cannot see, one cannot conclude that there has been a change of flavor in the neutrino. Then in that case, if you have not seen a change of flavor, your result is that your probability of your observed probability is smaller than some value, P. Okay? And then in that case, here you have in the parameter space of this using this formula. Here in the x-axis you have the sinus square root of theta, and in the vertical the mass split. So in principle, the formula may have the expression of the probability. We have this shape here. Okay, this will be the shape for a fixed value of the probability, like a contour plot in the parameter space. So then, if you have a negative result, so nothing observed, no oscillation, your probability is smaller than some value, then you just draw the contour corresponding to this p-value, and then the region you get to the right is the excluded region. So you can exclude all this parameter space. This is not a true value of the parameters, because if the true point was here, then you should have been able to see something in the experiment. And if you have not seen anything, it's because the parameters is not in all that region. So I'm sure you have seen this kind of parameters several times, in particular for the searches of sterile neutrinos. We will see tomorrow a couple of them. Usually these are very, very familiar. This also for reactors. So this is the result. And if you have, on the other side, you have a positive signal, you have observed like a transformation of one flavor to the other. So you have your observed probability with a central value P plus minus some error. In that case, you can define an allow region in the parameter space that where you think what is most probable that the true point will be. For instance, here, if you find one value of the probability that considering the error is given by this contour here, this should be the allowed region in the parameter space. Okay? So this is quite simple. So just to, if any of you is interested in doing some practical exercise, one can check in the case of, for instance, the Shaw reactor experiment. It was a reactor experiment in France that was trying to measure the antineutrino electron disappearance for distances of 1 kilometer. Okay, and it didn't find any signal. Okay, so it just got, with this experiment, one just got an upper bound on the θ13 mixing angle. Okay, so with this experiment, one can do a very, very naive analysis. For instance, it is quite safe to consider just two neutrino oscillations and consider just vacuum, because in 1 kilometer distance from the reactor to the detector, the neutrinos travel essentially in vacuum. So in that case, the ratio of the experiment was that they were measuring results consistent with no disappearance. Okay, so if they were measuring PEE, okay, so the results were consistent with 1. So essentially no oscillations. So this is more or less the same. The rate they were measuring, it was around 1. So no signal of disappearance. This is one example of negative signal. So one can do a very rough approximation trying to translate this result to the parameter space. One can assume that identify this ratio with the probability, okay, and trying to see what one can get. And also for the statistical analysis, one can do very rough analysis as well, just comparing the observed probability, this ratio equal to 1, with the one you get from the formula and assuming just the error. So here there is no background, there are no efficiencies. Once you do a simulation, you need to consider many, many things. Energy resolution, background, systematics, but this is just to let you know how this works at first approximation. So with this, you can get this region will be the excluded region for 90, 95, and 99 confidence level. So this region over here to the right will be the excluded region. You can do this you can do just with a very short code, just doing this analysis, and you will get this. Okay, and then of course it is not enough if you want to do precise things. If you want to do the full result of show data, also in show there were two reactors. You need to consider 2 reactors. You need to consider the finite energy resolution, and then you will get this this nicer plot. Okay, exclusion plot. But essentially, you get here. You see, since I put a finite energy resolution, these wiggles are averaged. As I was saying this morning, this disappear because of the finite energy of the resolution. Since this is very rough, here there was no information about that. But you can see that essentially the same order of magnitude for the excluded region you get it. And just to finish, let me show how this can be applied also to the case of solar neutrinos. In the case of solar neutrinos, we have several observables to analyze. So for instance, we have the neutrino survival probability that is measured in all the experiments. The radiochemical experiments were measuring just this. Then the more modern experiments were also measuring the difference between the events in day and night, and the events as a function of the energy. So this is what we have here: the day-night asymmetry, and here the spectrum. So then here you can draw your lines, your contours of isoprobability as a function of the mixing angle and the mass splitting. Okay, you have each line corresponds to a value of the probability. Here the same for the day-night asymmetry. So this is the predictions for the difference in the solar neutrino flux during night and day. And here you have also the measurement of the neutrino survival probability as a function of the energy, because there are some experiments like Super Kamiokande or SNO that were giving this information. Then if you put all this information together, you can analyze the neutrino data. And then I wanted just to show you this plot that I think is quite illustrative. So this is in the analysis when we were just considering the results from the Davis experiment, Homestake experiment. Homestake was a radiochemical experiment only measuring the neutrino survival probability. So if you can see, this is the log region at 90% confidence level. It reminds you the shape of the probability, right? The one here. Because essentially with Homestake, we just can constrain the probability. Okay. Then with Galex was also radiochemical. Okay. So again, we can only constrain the probability, but the difference is that the energy range of sensitivity was different. Galex was sensitive to energies above 0.2 megaelectron volts, while Homestake was sensitive to energies above 0.8 megaelectron volts. So this difference of energy makes this shift between the region allowed from Homestake and the region allowed from Galex. And then at the end, the solution is going to appear from the overlap of all the regions. So then I go fast. Super Kamiokande, you have more information because you measure not only the survival probability, this shape, but also the day-night asymmetry. And this is why we have a hole. We have a hole here because the values of the asymmetry here are too large compared to what Super Kamiokande measures. So this is excluded. And also here. Okay? Then we had the SNO experiment. Then SNO was even better because it was also measuring different energies with more precision and was also sensitive to the day-night. And then for the SNO is the orange region. So you see how we can go in and try to find a solution. At the end, the combination of all these solar experiments is that white region over there. This is the overlap between all of them. Okay. And at the end, so from this, you remember here we had like 9 orders of magnitude valid for the delta M sol. So now we have essentially even less than 1 order of magnitude, thanks to the combination of all the results. Okay, so this is why, just to show you how we can combine the different experiments to put more and more constraints over the parameter space. And I think this is just the last. Yeah. So I don't know if you want to comment on that. If you have some question on that or.
Other questions, comments?
Okay, so if any of you wants to try this very simple practical experiment and has any trouble, you can tell me. If you want, I can help you if someone wants to do it. Okay, thank you.
Thank you.
Let
Okay.
me rename you.
minutes for questions. Or so I show you the.
Okay.
Okay. Good afternoon, everyone. Welcome to our second student talk session. Our first speaker is Domenico Frattulillo, from the University of Naples, and we'll talk about Planck scale deformed relativistic transformations in curved space.
Hello, I am Domenico Frattulillo. I am a PhD student in Naples, and my talk is about Planck scale deformed relativistic transformations in curved spacetime. So, doesn't work.
Did work like a second ago.
So let's start with a brief introduction to Dsr theories. And in the last many years, many models with modified spatial relations have been considered. And here I reported an example with F, that is a generic function in principle of the energy, the momentum, and the mass of the particle. And here L is an inverse momentum invariant scale that we suppose to be of the order of the inverse of the Planck energy. In the next of the presentation, we will consider only deformations that are linear in the product of L times the energy of the particle, because higher order deformation terms will produce effects too small to be measured. So the standard Lorentz transformations are not symmetries of these modified dispersion relations, so we will not have relativistic theories. But if we want to construct a theory that is still relativistic, what can we do? We can deform the relativistic transformations that connect inertial observers in order to accommodate this new invariant scale, and so we will have Dsr theories, that means doubly special relativistic theory. Now let's start with this formalism to analyze a covariant formulation of the kinematics in a 1+1 dimensional spacetime, starting from the example of the Minkowski spacetime. Let's define the phase space variables x and t that are the spacetime coordinates, and pi and omega that are the conjugate momenta to the spacetime coordinates, that are defined by the following commutation relations that are the canonical one. Now we know that the Minkowski spacetime is invariant under the Poincare algebra, defined by the following commutation relations between the generators, where E is the time translation generators, P is the spatial translation generators, and N is the boost generators. And here C is the Casimir of the Poincare algebra in 1+1 dimension, that is equal to E squared minus pi squared. Now we can introduce an Newtonian constraint in the following way: the mass Casimir minus the mass squared of the particles, and we can use H as the Hamiltonian of our system, and it generates equation of motions in terms of an auxiliary parameter lambda in the following way. If we calculate the Poisson bracket of the Hamiltonian with a generic function f of the phase space variable, and we consider the on-share relation that is given by h equal to 0, we will call this f dot, that is the derivative of the function f with respect to the lambda parameter that we have introduced. And in this way, we can obtain the standard kinematics in Minkowski spacetime. But now we are interested in the deformed formulation of the kinematics in Minkowski spacetime, where modified dispersion relations are taken into account. We can do this deforming the Casimir algebra of the Poincare algebra in the following way. Starting from the Poincare algebra E squared minus pi squared, we can add terms that are cubic in the energy and proportional to the Planck length. And as we have said before, we will only consider linear deformation in this new deformation parameter. Now, if we consider the standard Lorentz transformation, this Casimir will not commute with all the Poincare generators, and so we will not have a relativistic theory. So how can we obtain a relativistic theory? We have to deform the Poincare algebra in order to have a vanishing Poisson bracket between the new Casimir that you have defined and the new deformed algebra of symmetries. A way to do this is, for example, considering the following deformed algebra that is obtained deforming the standard Poincare algebra, introducing deformations that are linear in the Planck scale. And in fact, if we use this commutation relation to calculate the commutator between the time translation generators, the spatial translation generator, and the boost generator with the Casimir, they will vanish. Now, in order to formulate the kinematics in this deformed spacetime, we have to represent this algebra in terms of the phase space variables in order to calculate the word lines of our particle. And a way to represent this algebra, representation of this algebra is an example of the representation of this algebra is the following one. Here, let's notice that P is again the spatial translation generators, E is the time translation generators, and then is the boost generator. And if we use the Hamiltonian formalism that we have introduced before, and so we calculate the commutator, the Poisson bracket between the Casimir and X, and the Casimir and T, this will be respectively equal to the X in the lambda and the T in the lambda, and so we can obtain the velocity of a massless particle if we set C equal to 0. And this is not equal to 1, but we have a velocity for the photon that is momentum dependent. So now let's consider the following experiment. We consider a soft and an hard photon with momentum respectively P soft and P hard, where P soft is much smaller than P hard. They are emitted simultaneously by a source according to an observer local to the source. And we want to calculate the time delay with which these two photons arrive to a distant detector, and we have called capital N the distance between the source and the detector. Now, if we calculate this time delay in the source reference frame, we obtain the following expression for the time delay. But, however, the time delay that we observe is measured in the detector reference frame. So we have to. So the previous result is not a physical quantity, it's not correct, because we have to recalculate this quantity in the correct reference frame, that is the telescope one. And if we do this, we obtain, in fact, a new result for the time delay that is this expression shown in this slide. And so let's understand what's happening. In the source reference frame, the two photons are emitted simultaneously according to an observer that is local to the source, and the two photons, the hard one and the soft one, will travel at different velocities, and so they will reach the detector at different times. But according to an observer that is local to the detector, the emission is not simultaneously, and this is due to the fact that we have deformed the translation generators, and so the action of the translation on the word line is momentum dependent, and so word lines with different momentum will be translated differently, and so we will have a relative locality effect, and the correct time delay is this one, and not this one that is calculated in the wrong reference frame. In this analysis, we have only considered two distant observers that are at relative rest. But the main sources used to test this kind of models are the GRVs that are not only distant sources, but they are also supposed to be highly boosted with respect to us. So what happens to the time delay if we also take into account the relative speed between the source and the detector? So we have to calculate how coordinates and momenta transform under a finite boost. And a way to do this is to solve this differential equation shown in this slide, where A is a generic function of the phase space variable. And so if we calculate the X index E, and the other differential equation, we can obtain how coordinates and momenta transform under this boost. Here we have called C the boost parameter. Then when the source is boosted toward the detector, it is greater than 0. And the time delay obtained is the following one, where we can see that there is an exponential suppression due to the boost parameter. In fact, we have said that C is greater than 0 with our choice. And so let's notice that in this formula, all the physical quantities are calculated in the detector reference frame. That is what we want to do. Okay. Now we have shown an example, a Minkowski example. So we have considered a flat spacetime. And now we want to also take into account curvature effect to the time delay. And the simplest way to do this is starting from the Dsr algebra, and we can deform the Dsr algebra in order to have a Dsr theory. This is the standard Dsr algebra of symmetry in 1+1 dimension, where H is the Hubble constant, E is the time translation generator, and P is the spatial translation generator, and N is the boost generator. And we will work in conformal time coordinatization. That means that we will call X the spatial coordinate, and we will use the conformal time eta that is related by the following relation to the comoving time that is usually used in cosmology. And we can also define pi and omega as the conjugate momenta to X and eta, and they are defined by the canonical commutation relations with X and eta that we have seen in the flat case. Now we can use the phase space variable x, eta, pi, and omega that we have defined to represent the Dsr algebra, and the standard representation is the following one. And we can calculate the Casimir of this algebra that is given by the following expression. And as in Minkowski spacetime, we can consider a covariant formulation of the kinematics, introducing the Newtonian constraint H that is given by the difference between the mass Casimir and the mass squared of the particle. And we can again use it to describe covariantly the evolution of a physical system. Now we are interested in DSR in the Dsr spacetime, and so we deform the Casimir of the Dsr, again introducing terms that are cubic in the energy and proportional to the Planck length. Now, to construct a relativistic theory, again we have to deform the algebra of symmetry in order to have vanishing commutator between the algebra generators and the mass Casimir defined before. And this is an example of algebra that is compatible with this Casimir in the previous sense. And this is a possible representation of the algebra that we have shown in the previous slide. And so we have all the ingredients to study the kinematics in this Dsr spacetime. And if we use the covariant conformalism that we have introduced before, again, we can calculate the velocity of a massless particle, and we obtain the following expression for the velocity of a photon that, again, it is not equal to 1, but it is momentum dependent. And if we integrate this expression for the velocity, we obtain the word lines that are given by the following expression, and these expressions are the same in all the inertial reference frame because we have a relativistic theory. So we can calculate, as in Minkowski spacetime, the time delay with which two photons, an hard one and a soft one, arrives to our telescope. And so, as we have seen in Minkowski spacetime, we cannot calculate this quantity in the source reference frame, but we have to act on the word lines with the deformed symmetries in order to consider the right reference frame, that is the telescope one. And here there is the result for the time delay that is calculated in the detector reference frame, and I have calculated this quantity in the limit in which e to the minus c is much smaller than 1, and this is because GRBs are supposed to be highly boosted in with respect to us, and so the boost parameter is supposed to be much greater than 1. And so I obtained this result for the time delay, where z is the redshift distance of the source. Again, all the quantities are calculated in the detector reference frame, and if we send h to 0, obviously this result reproduces the one that we have seen in Minkowski spacetime. Okay, I have finished, and so thank you for your attention. Yes.
There are also more like geometric. I don't know whether Tristan knows to answer better.
Okay, no, I haven't studied any other description. The only one that I have studied is this algebraic one. So I don't know if there are other solutions to do this. No, it's just a simplification because we are all interested in time delay calculation, and so I have restricted the analysis in the xt plane, and but there are no reason.
Other question?
Yes, first observer is the one that is local to the source, and the second one is the one that is local to the detector, and they are not only distant but they are only boosted of the detector. Yes.
And can you tell me what happens with the time delay if there is no boost?
If there is no boost, okay, this formula does not apply because it is in the limit in which e to the minus c is much smaller than 1. But yes, I found also the result where no boost there is. It is present also in the article, in the reference that I have shown. The result without boost is present in this reference. What? Yes, basically the main difference is that it is not suppressed by the exponential factor, and the dependence on redshift is given by a logarithm of 1 plus z, and another term that is of the kind z over z plus zeta squared. It's polynomial plus a logarithm.
Have two different momenta here. We have the p and the pi.
Yes.
Which one is
No.
the physical momentum of the particle?
Here p and pi are the same because I have represented the translation generator with pi. So there is no difference between p and pi. P is the translation generator, and I have represented it with pi, that is the conjugate momentum to x that have the
eigenvalues are different. Yeah, one is a function of the other. Right?
They are the same. Both are the index. P and pi are the same. Yes, I have chosen.
The energy and omega. Which one is the physical energy?
The physical energy is I think that is the charge associated to E, that is the nether charge of this. E is the time translation generator, and omega is the conjugate momenta to the conformal time. And when for the photon, the on-shell relation is pi equal to omega plus the correction of the
physical spatial time coordinates are not the momenta conjugate of the physical moment.
Yes. Pi and omega, yes, are the conjugate momenta, but P and D, yes, even if so, the time translation generator is not only the in the T, but it is.
I don't see any, so thank you again.
Can you hear me? Okay.
Okay, so this button is a pointer, the cell phone.
And this also changing the slide, so let me just, okay.
Okay, so welcome our next speaker, Maria Grazia and Luca from Napoli, and she will talk about quantum gravity phenomenology with multi-satellite telescopes.
Yeah. So, hello everyone. My name is Maria Grazia di Luca, and I am a PhD student. So, this talk will be about quantum gravity phenomenology with multi-satellite telescopes. And in particular, I will not go through the mathematical details because right now I'm more interested in presenting to you the perspective that we are proposing and that we think might become relevant for the future generation of satellites. So, okay, we know that quantum gravity phenomenology aims to account for the Planck scale physics effects using a bottom-up approach. In fact, even though no self-consistent theory of quantum gravity has been proposed so far, some common intuitions arise from different models, and a tentative phenomenological description of such features might lead to testable predictions. Again, as we know, the energy scale that is typical for this correction, so at which we expect this correction to become relevant with respect to classical gravitation, is given by the Planck mass, which is much larger with respect to the energies that we can currently access in accelerators. And for this reason, our universe represents the most promising resource that we have. In fact, the mechanisms of production and propagation of high-energy cosmological messengers could hide some footprints of quantum gravity, and in particular, they could give us access to these high-energy regimes that we are interested in. In particular, the recently proposed technology of multi-satellite telescopes is a very important chance in this perspective. What are multi-satellite telescopes? Systems of hundreds or possibly in the future even thousands of small satellites in orbit around Earth, all communicating with each other and with the ground itself. And so they represent a completely new tool for doing space science directly from space. Multi-satellite telescopes are characterized by very reduced costs, both in the production, because a large number of telescopes enables a standardization procedure in the production, and in the launch, because the launch costs are proportional to the masses themselves. And so it will be possible to construct through constellations of satellites around Earth, and so to reach baselines which are obviously much larger with respect to the ones that are allowed by ground-based telescopes. In particular, Hermes will be a Pathfinder experiment to be launched by the end of 2022. It will only have 3 nanosatellites, and it will take measurements in the KeV, MeV range. But among its goals, there is exactly the one to to probe the space-time granularity down to the Planck scale. And in particular, this will be followed in 2050 by the Grail Quest, which is a mission concept with a fleet of hundreds or even thousands of these small satellites. So let us briefly recap how such telescopes can actually measure angles, because we want to stress that the large baselines that will be reached will improve very much the sensitivity in angular measurements. So consider a distance source for which we can apply the plane wavefront approximation. We stick to a 2+1 dimensional case for the simplicity of the geometrical construction. So we will need at least 2 satellites to determine the direction of this source. In particular, if we call alpha the angle between the propagation direction and the direction in between the 2 satellites, then we can estimate alpha because the time that is required for the signal to propagate from the satellite A to the satellite B is simply given, if we put C equal to 1, by the distance between the two detectors projected along the orthogonal direction with respect to the propagation direction of our photons. And delays between the arrival of the signal at the two detectors can be easily estimated by considering cross correlation between the two signals. So for example, here I reported a typical light curve for a GRB as it would be seen from the satellite A and from the satellite B. And the precision in the angle measurements will increase as the square root of the number of satellites. So now, in the context of quantum gravity phenomenology, such high resolutions could lead to significant tests of tiny angular effects, because we expect that any quantum gravity effect is suppressed by our energy scale, that is the Planck mass. So let us consider one prediction that is known in quantum gravity phenomenology and associated to angles, known as dual lensing. So when considering deformed dispersion relations, and in particular in the context of doubly special relativity, we accordingly deform boosts in order to have a generalized relativistic principle, so to have the Casimir invariant. Then what happens is that if we have a source, so again, we consider the 2+1 dimensional case for simplicity, and a source that emits two massless particles, so for instance photons, one of high energy, here reported in blue, the hard photon, and one of low energy, here reported in red, the soft photon, under the same spatial direction. So here we see the projection in the x1, x2 plane, and this is the angle with respect to our x1 axis. Then in a boosted frame, what happens is that the spatial projection of the directions of the two photons will not coincide, and in particular there will be an angle between these propagation directions that is proportional to the difference in energy of the two photons. So if we neglect quantum gravitational corrections for the soft photon, essentially this effect will be proportional to the energy of the hard photon. Now, what does it mean? That if we have an observer that receives the soft photon, so whose reference frame is boosted and translated in order for the soft photon to cross its space-time origin, so essentially this special relativistic, we are saying that the detector is along the light cone, the future light cone of our soft photon, then the hard photon, since it propagates in a different direction, will not even cross the spatial origin of our detector, and so there is nothing to measure. So this kind of description of dual lensing that we find in literature is not suitable for detectors that are made of point-like satellites. So which is the perspective that we propose? In the source reference frame, we do not consider two photons emitted in the same direction, also because we have no way to understand whether these photons were actually emitted in this direction, since we have no local measurements at the source. And we consider a soft photon that is emitted in the direction of our observer, and the hard one which is emitted in an arbitrary direction that we constrain, requiring that it will cross the spatial origin of our detector. So in this new perspective, we don't have two parallel photons, but we have two photons which are detected by the same observer. And we perform again the calculation for dual lensing. So we ask if these two photons detected by the same satellite will still arrive with a different angle. And we find that the answer is yes. So there still is a delta theta, a different arrival angle for the two photons, which is proportional to the energy of the hard one. So now, let us get back to the triangulation procedure. In the special relativistic case, we only have one wavefront, so all photons, no matter what their energy is, propagate in the same direction, and the signal travels with a travel time that is just L times the cosine of alpha. When dual lensing is involved, instead, what we expect is that soft photons and hard photons belong to different they propagate with different directions and wavefronts, since they come with different angles, and so the time needed to go from one satellite to the other will depend on this direction and will in principle be different. So if we can measure the time for the soft signal to go from A to B, and we are sensitive enough to measure the time for the hard signal to propagate from A to B and to actually find the difference, we might detect a signature for quantum gravity. So which is the value for this new time delay? Here I don't report the full expression because our results are still preliminary. But what we see is that all the ingredients that contribute to these corrections to the time delay are the ones that we might expect from both dimensional considerations and from physical ones. So first of all, we find that the quantum gravity energy scale, the Planck mass, is again adimensionalizing the energy of the hard photon. So again, the higher the energy of the hard photon, of the hard wavefront, we could say, the less suppressed the effect will be. Then, for example, with respect to dual redshift that Domenico previously described, that is a longitudinal effect. So the dimensional the dimensional amplification is given by the distance from the source to the detector. In this case, our effect is angular, and so it's a transverse effect. And this means that it will be amplified by the distance between the two satellites. And so now we understand how important it is to reach larger and larger baselines. Finally, we computed the transformations of our word lines at all orders in the boost parameter. So we considered finite boost transformation because we wanted to understand whether a large boost could actually be an amplifying factor. And we find that as we might expect from special relativity, the dependency on the boost rapidity is exponential. So yes, if we choose the right sources, then this effect might be actually testable. What are the future perspectives? So of course we need to refine our calculations, and in particular to consider different scenarios of dual lensing, because we want to obtain a result that is obviously model independent. Then we need to consider the physical case, that is the 3+1 dimensional one. So two angles will be involved, and we need to understand how those two angles are affected. And finally, we need to consider other possible physical observables that are actually testable at multi-satellite telescopes. So one of course is the usual time delay in the propagation, and to see how much we can constrain from observation of different effects our theory. So thank you very much for your attention.
We have time for questions.
Yeah, well, the point is with ground-based telescopes, you might have baselines of the order of kilometers, while, for example, even for Hermes that will be in low orbit, we can reach baselines of hundreds, thousands of kilometers. So we will gain a factor 2, even a factor 3 in order of magnitudes. And those are precious because we are talking of very tiny effect. So this is the main idea for having a multi-satellite telescopes with respect to, something like IceCube that will be, capable to track the photon, and so might give a different measurement for the angle, but no amplification. Sure. Yeah, of course, that's the objective. That's one of the goals. And with Hermes, the precision will increase of maybe 1 or 2 orders of magnitude, and also the actually portion of the sky that we have access with Hermes, it's quite reduced. But with the Great Quest, we believe that we can gain several order of magnitudes in the precision with which we measure angles, because as I said, it grows as the square root of n. So obviously having hundreds of satellites will increase of a factor 10 and so on. So of course, like 10 to the minus 3, even 10 to the minus 5 degrees, and that's the precision. 3, like again gaining 3 or 4 orders of magnitude with respect to the Yes. Yes, of course, it doesn't mean that we can access the Planck scale, but as our preliminary results show, we have amplification in the boost parameter as well. And so for highly boosted sources, we can gain other 3 or 4 orders of magnitude, and then we can get closer to it. So obviously it depends on the sources, because it depends on the boost. That's the main ingredient that we will need to account for in the sources.
Okay, other questions? Something about the spectrum size of the
Sorry, can you repeat? I'm a little closer.
First of all, in terms of the vector itself, what does it mean? And in let's say final form, what is it? I think that's order of 100 satellites.
Even thousands. Yes.
Then what's the size of those satellites, and what is their pricing formula?
Okay, so for example, for Hermes, the satellites will be the so-called 3U. So let me get back to the slide. Maybe I'm too far away. Okay, so these are the specifics for Hermes, and then obviously for the Great Quest, there will be obviously an improvement. So each of these 3U nanosatellites will be parallelepiped of 30 times 10 times 10 centimeters. So very small satellites, each one with a reduced capability to measure energy, but the idea is that having hundreds and thousands or thousands of them, we can achieve better results. So, yes, and it will be in low Earth orbit, so the 300.
What sure you thought of that, but as an observer operating from the ground, you have this problem that happens when Elon Musk wants. So I'm wondering, how is it going to affect ground-based observations in optical bands?
Yeah, actually, I don't know this. Maybe I'm not the best person to. Yeah, no, I'm sorry. I don't know this because mainly I work on the theoretical side. So I did my researches on how these satellites will work because I wanted to, to do my calculations in order that they are relevant for the kind of measurements, because dual lensing in literature is something that is treated from a very theoretical point of view. So there is no actual interest for now in how to measure it, because it was also the calculations were the first order, and so there was no amplification, and so there was no interest in it. And what I did was asking myself, okay, with multi-satellite telescopes, maybe this will not be tiny anymore, will not be under our sensitivities. So which is the physical quantity that we are interested in? So that's why I present all the details about the satellite, but of course I don't work on that. So I'm not the best person, sorry.
One more thing, I understand you cannot comment on that, but I'm also a bit concerned about the collection area. But you want to observe hard X-ray and soft gamma ray. Those are rare events, let's say, and you have 100 centimeters squared. That's not a lot of high probability of catching anything. But okay, I'm sure there is a proof for concept.
Yeah, the fact is that this band, that is quite a small band, and also it's in the soft part of the gamma spectrum, will be the one for Hermes. But then for Grail Quest, they will try to enlarge it. So the main idea is that Hermes will be quite finder for it. So then, of course, the true access to these effects will come with Grail Quest.
Yeah, thank you for the report. And then we come to our next speaker, Fabian Wagner.
All right, can you hear me? All right. Where's the pointer actually? That's the pointer. And here, okay, that works. All right. Hello, everybody. For those to whom I've not introduced myself yet, first of all, sorry. My name is Fabian Wagner. As was just said, I'm a PhD student from the University of Szczecin. And let me first, of course, thank the organizers for creating this wonderful school, especially at this wonderful place. It has been, I mean, it's now coming to an end and has been quite long, so I will try and be not too technical here and just show you some ingredients of what I've done here. In particular, I'm going to present work I've done in collaboration with my supervisor, Mariusz Dąbrowski, and Luciano Petroziello from Salerno. The title of the talk is, as was said, curvature-induced uncertainty relations. That is, uncertainty relations which are kind of changed by curvature itself. In particular, I want to address the question, are extended uncertainty relations of quantum gravitational origin. Those are claims that have been made in the literature in the past. If you don't know what extended uncertainty relations are, I'm a bit loud, ain't I? It's okay. If you don't know what extended uncertainty relations are, that's not a problem, no worries, I'm going to explain it. So in order to tackle this question, I divided this talk into 4 points. I'll introduce you to the subject, then show you the approach we took in our work to then give the results and try and answer the question I just posed in the discussion, okay? Let me start with the introduction. Okay, now it disappeared. Okay. All right, I guess all of you have had the Robertson-Schrödinger, or in this case, Robertson relation in your undergrad studies when you were having your first quantum mechanics class. This relates, of course, the standard deviation of two quantum mechanical operators, say A and B, to the expectation value of their commutator. And the most famous version of this is, of course, the Heisenberg's uncertainty principle. If you choose basically position and the momentum operator, and you get this relation. Of course, then you understand those as the spreads in position and momentum space, which are inversely proportional to each other. Okay, I guess all of you know that. Now, in the last, say, 20 to 30 years, this idea that there is a minimum length scale somehow underlying everything coming from quantum gravity has been quite, or has become quite prevalent in the phenomenology community. This is, I mean, related to DSR, where you have a maximum energy scale. That's the other idea, or, you know, this fixed energy scale. In this case, you just say, okay, whenever we measure something, right, the length scale we can approach will never be smaller than some length scale called L0, and supposedly this is, of course, of the order of the Planck length. One way to possibly implement that, very simply, just into non-relativistic quantum mechanics, is by kind of changing this uncertainty relation we just saw before and adding this green term here, right? Which depends here on the standard deviation of the momentum operator. If you do that, your quantum theory will automatically contain a minimum length. This is not, so this is called usually generalized uncertainty principle in the literature, but this is not what I'm talking about today. It's just kind of the more famous cousin. But what I'm going to talk about is more the idea of minimum momentum. In particular, we all know there is a cosmological horizon, right? Which gives kind of a maximal scale to wavelengths in a way. Wavelengths couldn't, or which we can approach, cannot be larger than that, and that corresponds to a certain momentum scale, which will have a minimum here to be related to the Hubble horizon. You know? Again, one way to implement that is by add a term which is completely analogous to what we heard before, just that here, this will depend on the standard deviation of the position operator. Now, as I showed you before, the Robertson-Schrödinger relation, changing this means changing the canonical commutators. So you're modifying your quantum mechanics altogether, and you introduce these scales. But yeah, this is what you do here. And this is what you call extended uncertainty principle. So now we're here. Now the question is, of course, here, the horizon is a curvature-induced effect. And we shouldn't need to have to change quantum mechanics to describe this, in my opinion. Because, I mean, quantum field theory in curved spacetime should be enough, or in this case, quantum mechanics in a curved space. And thus, we might as well ask ourselves, is this the only possible formulation? Of course, if I ask this question, the answer will be negative, because this is what we did, and this is how we kind of approach this is what I will explain now. Just imagine as a picture, the single slit, that's where the inspiration, I guess, comes from, is if you have some kind of wave packet coming in at some side and it's scattering off a slit, the slit width, call it delta x, can be understood as the uncertainty in your position, right, afterwards. And many arguments in this relation have been done basically in the 20s. If you have some other measure, if you have momentum uncertainty, you set it somehow equal to h bar, and that's how you originally got to uncertainty relations. Now, of course, this is all quite sketchy, but it can be made rigorous. And this can be generalized in a way to curved three-dimensional space. And this is where we come in. It's not my idea. This was published in 2018, and we kind of developed this quite much further. So what you start with is that you kind of constrain your quantum theory to a compact domain by imposing Dirichlet boundary conditions on the boundary of this domain. If you do that, your particle, whatever you're describing, your system, will be localized within this domain, right? And this tells us that if we can calculate kind of the size of this domain in a diffeomorphism variant way, for example, for its volume or whatever, then this length scale, call it rho, will give you a measure of your position uncertainty. That's the idea. Then on the other hand, it is possible to kind of get a scalar momentum operator. If you kind of use, Dirac / notation, you get a scalar out of everything, and you can then define the standard deviation of the momentum operator also on the curved space. This is what you do, I mean, just as you do it usually, and it really means that your momentum operator has to be described in an orthonormal frame, or in this case, a local Euclidean frame. That's the idea. Now, this is the setup, basically. We're putting this on our curved background, right? It can be shown then that this standard deviation will have a global minimum. Okay, for some state, call it psi naught, right? And this is bigger or equal to 0. In particular, it's a function of rho. And if, our measure of momentum uncertainty, this standard deviation is bigger than something which is a function of our measure of position uncertainty, this is what we call an uncertainty relation. And this is what we want to obtain. Right? Now, which domain we choose, of course, is somehow arbitrary. This will just change our parameters somehow. But we chose just the simplest one, which is a geodesic ball. I guess most of you know what that is. You just connect your center, call it P naught, to the boundary by geodesics to all directions, and then stop at some radius, call it rho, right? This is the geodesic distance, which is smaller than rho. And then, you have a geodesic ball. The radius of this geodesic ball is diffeomorphism invariant, so you automatically get your measure of position uncertainty like that. Now, of course, everything that is topologically a ball will be somehow a geodesic ball that depends on the system of coordinates. Here, for example, you can see how this gets deformed as such a geodesic ball is approaching a black hole horizon from a static point of view, basically. And but yeah, that's basically all the setup. The background now is, of course, what is interesting. We start at the Lagrangian of a relativistic particle, general relativistic, so on a curved background, and describe the background metric according to the ADM splitting that has already been talked about a lot here. So in terms of, the lapse function, the shift vector, the induced metric, right? And from there, we can take the non-relativistic limits, which of course introduces a preferred frame, but I mean, that's what a non-relativistic limit anyway does. Now, then we get some effective fields here, effective pre-metric, which gives us some kind of background curvature or background curvature for space, and an effective vector potential, which also couples to the momentum as, like a minimal coupling, basically, just as couples to the mass, of course. And all of these fields are necessary to define your momentum operator in a good way. If you do all of this, once you have defined it, you can do all the calculations. There's just one more thing that's missing. We assumed that these geodesic balls are small. This means that, of course, or measure or position uncertainty is small in comparison to the background length scales introduced by the curvature. And then what you can do is that you describe your ball with Riemann normal coordinates. That is, you have a flat metric inside plus some curvature induced corrections which depend on the Riemann tensor, and then you can do everything perturbatively. That's the idea. So let me come to the result then. Right. Okay. Here we see the uncertainty relation we obtain. First of all, of course, on the left-hand side, we have both measures of uncertainties multiplied, as we usually do. Then, of course, the flat spec result is not the same as usually. It's a pi h bar, but then this is not the same kind of uncertainty relation as the usual one. Okay, shouldn't come as a surprise. Now, the important part here are, of course, the corrections, which you can see basically in green. And there's, first of all, here, the Ricci scalar of the effective metric, which we have on our hypersurfaces, right? And the gradient of the shift vector, which is related basically to background or rotation of our background metric, right? Now, you might think that, of course, the second term is kind of a fourth order because we have a row to the 4 here. So, position uncertainty to the 4, but it's not. It's of second order in the same way as this one, because our lambda c, which is the quantum wavelength of the particle or the system we're looking at, right, is kind of, if you look at that, in a non-relativistic limit, this is much bigger than 1. So, this is actually of order rho squared. Okay. Now, psi here is just some number. You can see up here, it's just a mathematical constant. Anyway, if we have positively curved slices, this means that our uncertainty decreases. Well, if we have negatively curved slices, the opposite is the case, right? An example of how this then plays out may be shown, for example, for a rotating black hole or a body, say a particle which is kind of orbiting around the Earth, or we have this kind of Kerr system. So we're describing, of course, everything with the Kerr metric, and obtaining the following result, or obtain the following result. On the left-hand side, it starts. On the left-hand side, you can see the orbit of the particle. This white point is the horizon, so this better be a black hole, I guess, but it's still everything non-relativistic, so it works. And on the right-hand side, you see the deviation from the standard uncertainty. You can definitely see the closer the particle gets to this horizon, or the stronger the curvature gets, of course, the stronger our deviation becomes. This is, I guess, what would have been expected in this case, right? Now that we got all the results together, let me get to the conclusion. I asked in the beginning, are extended uncertainty relations of quantum gravitational origin? The question is here, did I use any quantum gravity? I did not, right? I mean, I obtained all of this result just on the assumption that we use quantum mechanics on a curved background. That's everything. So it seems that we really don't need that curved spaces are actually enough. We don't need to modify quantum mechanics in this way to get, for example, something like an extended uncertainty relation, just when we're like looking at really the Fermorphism variant uncertainty relations, okay? So to summarize, we get our extended uncertainty principle as a semi-classical result. As I said before, we increase our uncertainty for negatively curved slices, or do the opposite for positively ones, and for a non-vanishing shift gradient in this case, right? What I didn't show you here is that, in fact, we can omit the relativistic limit and do the same treatment, even though, of course, we still kind of introduce a preferred frame by choosing where the geodesic ball looks like a geodesic ball, right? But still, this works at relativistic velocities as well. Anyway, what is, I guess, most interesting for the future is that you can start with the same derivation on a curved momentum space and on a curved position space. You can do basically exactly the same stuff, and what you will obtain will be a generalized uncertainty principle. And this kind of relates these ideas we have of a minimum length with curved momentum space, similar to what has been, of course, obtained in doubly special relativity. And this is probably where then the next work is going to go. So this was it. Thank you very much for listening. I didn't say. P0 is, no, I forgot to say that. That's the center of the ball. So it's just the position of the particle. Okay. Okay. No. In this case, it's a point. P0, a point. I'm sorry, no, I forgot to say that. Of course, when you do the Riemann normal coordinate expansion, you expand in a point, right? And of course, the best thing to do is to expand in the center of the ball, right? And then you, yeah. I mean, the size of this correction, of course, just depends kind of, what you see here is that this is basically your curvature length scale squared, and you divide rho squared by this length scale squared. That's how you can estimate quite simply what it is, right? Like if you, this effect is, for example, of course, it's tiny for the cosmological horizon. But I mean, people have been doing this in extended uncertainty principles for a while. And this, for example, would also exist just from basically orbiting the Earth, for example, and the effect would be larger. So kind of this calls all of this a bit into question. Yeah.
So at the beginning, you were stressing the fact that you had different environments, right? And then you said you were going to take the non-relativistic limit
on free space.
On
the diffeomorphism variance on free space, not in four space.
Okay, so yeah, I
for
thought
three-dimensional space. No. Yeah, because generalized uncertainty principles, extended uncertainty principles are working in quantum mechanics, like single particle or several particle quantum mechanics. So this is all non-relativistic. This entire area, actually. Yeah.
Okay, thank you. I think we need to go on.
Mm-hmm.
Next one. Thanks.
No, it's called Corfu2021 or something.
Oh,
yeah.
Okay.
Yeah. Mm-hmm. Yeah, thank you. So yeah, I'd like to thank a lot the organizers for giving me the opportunity to give this talk and for like hosting us to this great school. I know that in the program it says like developments in teleparallel gravity, but I mean, I thought, why talk about developments if not many people know what teleparallel gravity is? So I decided to do an introduction to teleparallel gravity. I'm Konstantinos Dialektopoulos and I'm a postdoc at the Aristotle University in Thessaloniki. So the overview of my talk is going to be like this. I'm going to start from showing you what the geometric trinity of gravity is, which is in fact three totally equivalent descriptions of gravitational interactions. One of them, of course, is GR, and the other one is the teleparallel equivalent of GR. And there's the third one, which I will not describe in this talk, but I will mention it. It's the symmetric teleparallel equivalent. And I'm going to give you some more details about what this teleparallel equivalent of relativity is. I'm not going to present my results per se, but the talk is based on one recent paper that I wrote with some colleagues, one of whom is here, Sebastian. And of course, if you want more details, you can either send me an email or go there and read it. So let me start. Yeah, in general, a manifold in differential geometry is described from by a metric and a connection. These two quantities, let's say, are independent with each other. They are not in principle related, even though in GR they do. The most general connection that one can write down has this form. So this is the first gamma is the Levi-Civita connection. The second, this kappa is called the contortion tensor, and the lambda the distortion tensor, and all of them have this form. So this gamma is the known Levi-Civita connection. Kappa is related to the torsion of the spacetime, or of the connection of the spacetime, more precisely. And L, the distortion tensor, is related to the non-metricity of the connection of the spacetime. The torsion is given from the difference of from the antisymmetric part of the general connection. And of course, the non-metristic tensor is known as the covariant derivative of the metric. Another property of the connection is, as you know, the curvature of the space-time. Physically, what this means, this is a nice schematic way to represent these three tensors. So in a purely in a space-time, in a manifold which is governed only from curvature, no torsion, no non-metricity is there. If you parallel transport a vector along itself, then the difference here will be analogous to the curvature of the space-time. That's what we all know from GR. Now, if we have a space-time which is flat, so there's no curvature there and no non-metricity, there is only torsion. If you parallel transport one vector along another vector, the parallelogram will not close, and this difference will be proportional to the torsion of space-time. Analogously, if you have a space-time with no curvature and no torsion, the non-metricity will give you a difference in the length scale of the vector. Here you can see in a very nice plot all these theories. So the most general one, as I showed, including all of the properties of the connection, both curvature and torsion and non-metricity, is the metric affine theory, of course. And if you take specific properties of the connection to vanish, you end up with the three different representations. Like if you go and take the curvature to be non-zero and the torsion and the non-metricity are zero, you end up with Riemannian geometry. If you take the curvature and the non-metricity to be zero, you end up with the Vacuum-Box geometry, which is the one I'm going to focus now. It's called the teleparallel geometry. And the symmetric teleparallel one is where the curvature and the torsion are zero and the non-metricity is not. Yeah, let me start. Of course, we all know that, but in order to compare it later on with the teleparallel equivalent, in GR, Einstein assumed that the connection is symmetric. So this is just an assumption. It's not somehow derived from somewhere. The fact that it is symmetric, it means that, I mean, all the antisymmetric part obviously is zero, so there's no torsion. And also another assumption is that there's no metricity in the space-time, which means that in fact, the general connection will have the known form of the Levi-Civita, the Christoffel symbols, actually. And the action of the theory is given by the simplest scalar that one can construct, which is the Ricci scalar. And of course, all the information needed here, I mean, since the Ricci scalar depends on the Christoffel symbols, and the Christoffel symbols depend on the metric, then all the information is encoded to the metric. Yeah, I remind you here that the Ricci scalar, which creates a couple of problems actually, depends on second-order derivatives of the metric, and that's why we need to add the Gibbons-Hawking boundary term to calculate to vary the action and find the correct equations of motion. Oh, okay. Varying the action, we indeed get the equations of motion, where here we have the Einstein tensor, and in the left-hand side, in the right-hand side, sorry, we have the arbitrarily defined, let's say, energy momentum tensor like this, and the geodesic equations for the particles are given by this equation, and this means, in fact, that as the common expression, let's say, that matter tells to the space-time how to curve, right? And not from this thing here, and also the space-time tells matter how to move. Going to the teleparallel equivalent of general relativity now, imagine there's no curvature, there's only torsion. So the connection of the space-time is purely antisymmetric, and the antisymmetric part defines the torsion tensor. And the relation between the torsion scalar and the Ricci scalar is only by a boundary term. So you can imagine that if you plug this into the integral of the action, then this boundary term will not contribute at all, and we'll have only, in fact, the equivalence between the two theories. And by varying this action, we get the equations of motion for the teleparallel equivalent of relativity. And this left-hand side is just the Einstein tensor written in the teleparallel format, where the fundamental field is this E here. So yeah, this is the inverse of the tetrad. And this is the fundamental field describing the gravitational field. In comparison with the previous, with GR, we can see here that the motion of a particle is described from this equation, which is not a geodesic equation per se, but it looks more like a force equation because it reminds us, for example, the Lorentz equation in the electromagnetism, because here this K is exactly, I mean, it describes exactly the gravitational interactions. And this gamma is the teleparallel connection. So yeah, some basic concepts. As I said, the fundamental field is the tetrad. The tetrad is associated with a metric from this relation, or the inverse metric and the inverse tetrad. The tetrad satisfies some orthonormal relations. I mean, these are known even from GR. I mean, GR can also be written down in this language. And the teleparallel connection has this form, where this omega is just a Lorentz connection. It's a spin connection. And in fact, is lambda d lambda is it's a gauge freedom of the theory, and we can always, at least locally, select it to be 0. The relation between the teleparallel connection and the Levi-Civita connection is just, I mean, the difference between them is the contortion tensor. Yeah, the action of the theory is just the torsion scalar, which is not taken a priori in order to look like GR, I mean, to reproduce GR's results, but it's derived from first principles. And this is because teleparallel gravity is a gauge theory of gravity, is the gauge theory of translations. And in fact, the torsion tensor is the field strength of the gauge potential. Yeah, I'm going to stick on the qualitative results here, and I'm not going to discuss more technical details about the theory. But just so you know, there is also another description, the symmetric teleparallel gravity, which is described only by non-metricity with no curvature and no torsion at all. Okay, of course, the equivalence between TGR, the teleparallel equivalent of GR, and GR are exactly the same. So at the level of equations of motion, classically, we are not able to distinguish between the two. However, because teleparallel gravity is a gauge theory of gravity, could even survive without the equivalence principle. So if at some point we find that, I don't know, at some energy scale, there is some violation of the equivalence principle, this theory could survive, while GR, of course, would crash. And yeah, for those of you who do know the Einstein-Cartan theory, which has both curvature and torsion, do not confuse this teleparallel gravity with this one, because they're totally different. So yeah, if they're equivalent theories, why should we bother? And the thing is, yeah, as I said, the universality of free fall. If somehow the equivalence principle is violated, GR will not survive, while TGR could. In addition, there is believed that TGR links to the Newtonian gravity better in the weak field limit, because both have this property. So Newtonian gravity could also survive without the equivalence principle. Yeah. Also, GR is, as we know, a geometric force. Let's say is geometry. In the contrary, TGR, the teleparallel equivalent, because it's a gauge theory, it looks more like a force. As I showed you before, it looks like the Lorentz force, and this means that it could somehow be integrated with the three other interactions in a better manner. Yeah. Apart from that, the energy momentum tensor, even though in GR is defined from the variation of the material action with respect to the metric, in teleparallel equivalent of GR, because it is a gauge theory of translations, it comes up as a gauge potential, as the nether current of the translation. So it's not arbitrary, it's not a pseudo tensor anymore. It looks like a space-time tensor. And apart from that, as a gauge theory, it differs from U1. Well, Young-Mills is non abelian anyway, but the difference from U1 in the sense that it is built in the tangent bundle and not in an internal bundle as other gauge theories, but it still keeps all the properties of gauge theories. So here I show you all the geometric trinity. GR is described only from curvature, TGR only by torsion, and symmetric TGR only by non-metricity. And the relation between these, I mean, here you can see the Ricci scalar expressed with the Levi-Civita connection and the torsion. Here the Ricci scalar and the non-metricity, and here the torsion and non-metricity. So they all differ for a boundary term, by a boundary term. And you can see that, of course, if we put it in the action, this boundary term does not contribute, and that dynamically all these theories are equivalent. And apparently, we have, of course, some advantages describing this, studying these theories. Of course, the gauge structure is one of them. It is said, it is believed that in some modifications, of course, of these teleparallel equivalent, like f of t theories or scalar torsion theories and stuff like that, there may be black holes, or I don't know, singularities could not exist. As I said, the relation with other fundamental forces is better formulated here because of the gauge structure. And also, there is a separation between gravity and inertia, because as I showed you in the motion of in the equation of the particle motion, the gravity was in the left-hand side acting like a force, while the inertial effects were in the left-hand side. Yeah, there are, I mean, plenty. The literature has plenty modifications, I mean, studied. Also, the review I showed you in the beginning studies all of the modifications in the literature, not the non-metricity related ones, but the torsion related ones, like scalar tensor theories, like teleparallel Horndeski theories, I don't know, many theories. And of course, the phenomenology is much better, much different, I would say, not better, particularly. And apart from that, in order to relate it with the topic of the conference as well, it would be very interesting to see how to quantize this formulation of gravity. I mean, there are a couple of attempts in the literature, but not all of them are complete. So yeah, you would know that, I guess. So yeah, thank you very much. Yeah, in the sense that, for example, the energy momentum tensor is defined as a gauge current, as a nether current of the translations. Well, gauge theory, indeed, as a general relativity, sorry, as a gauge theory of deformed cannot have, for example, such a specific definition of the energy momentum tensor. Apart from that, the gauge theory, in the sense that it looks like a force, right? I mean, yeah, compared to U1, for example, it resembles more to U1 than, I don't know, any other gauge theory. No, I mean, pure teleparallel gravity, the teleparallel equivalent of general relativity, predicts exactly the same things as GR does. So the equations of motion are exactly the same. They're second-order field equations, but instead of a metric, you have a tetrad. Now, of course, if you go to modified theories of gravity, you do have such, yeah. And not only this, but also, for example, in F of R gravity, we have fourth-order field equations because of the fact that the Ricci scalar depends on second-order derivatives of the metric. while in f of t, we have second order field equations because the torsion scalar depends only on first order derivatives of the tetrad, which means that you can even construct infinite contractions of the torsion tensor. You can put them in the action and still have second order field equations. Well, apart from the singularities, I mean, singularities are there because in TGR, in the teleparallel equivalent of GR, because they are exactly the same theories with GR. All of the rest are advantages of TGR as well, not only of modifications.
Then if the two theories are entirely equivalent,
it's because of the gauge structure. So you can have different masses. I mean, the particles could behave differently, different inertial mass and different gravitational mass, and still this theory, because of the gauge structure, would survive.
Okay, thank you. And our next Fotios Anagnostopoulos. Okay, we will talk about observational constraints on f of q cosmology. Please.
Hello to everyone. For those I hadn't a chance to introduce myself, my name is Fotios Anagnostopoulos. I'm now a postdoc in the University of Peloponnese. However, this is the old affiliation. I will talk to you about a new cosmological model that seems to be better than lambda CDM in some cases. Okay, this is a bold statement. I understand. Mostly chance for a debate. Okay. This work was based on a paper, this presentation was based on a work along with Vasilakos and Manos Aridakis. This is the outline of the talk. Okay. The status quo in cosmology today is that lambda CDM is well established. And there are many observational probes to test it. And this has been done thoroughly. However, there are some problems regarding, first of all, the value and the exact value and the physics of the cosmological constant. Secondly, the coincidence problem. And in more abstract level, there's a problem regarding the number of physical mechanisms that one needs to invoke in order to save the phenomena. For example, we need dark matter, we need inflation, we need dark energy. Apart from all this, there is some observational, let's say, tensions or problems or whatever you like, with the most notorious to be the Hubble constant problem. What is this? There's a direct measurement of H0, and it's found to be 74 kilometers over seconds over megaparsec. Now, from Planck, this value imposing lambda CDM is about 4.4 sigmas away, and this is an open question. Okay, one of the possible approaches to alleviate one or more of the aforementioned problems is the modified gravity. Now, Konstantinos Dialektopoulos said many things about one of the possible ways to modify gravity. Why to bother again? We'll bother because we can explain some stuff probably. Even we can probably describe jointly dark energy and dark matter, possibly, or at least part of the dark matter. Okay. Again, as Costa said before, there are three fundamental geometrical entities. Curvature, torsion, non-metricity. There is possible to formulate an equivalent theory to general relativity based on torsion and also based on non-metricity. The modified Feynman equations are equations 1 and 2, given a general FQ modification. FQ is a function of Q. Q is the scalar of non-metricity, which in a cosmological spacetime it's given as 6 times h squared, where h is the Hubble rate, the main observable in cosmology, or at least observable. We cannot observe anything directly in cosmology. Okay, for a particular choice of f of q function, we can have lambda CDM. Perturbation analysis gives this equation, equation 3, which is different from the respective one from lambda CDM only in G. The Newton constant is now a modified Newton constant according to equation 4. There are some proposed f of q models in the literature. Our model is the exponential one, equation 5. Okay, the main idea is to implement a more general model than the power law of usual Lascaux and Falzano. Another interesting feature of our model is that it has the same number of free parameters as GR, which is observationally very desirable. There is a GR limit without lambda for large redshifts. So we evade the BBN constraints easily. At the BBN area, we have pure GR essentially. And the Feynman equations for the particular model reads as equation 6. So this is an algebraic equation. We need to solve it numerically for particular choices of the parameters. Further, considering explicitly no lambda CDM limit, that is lambda different than 0, and then at z equals 0, we have this particular expression for lambda. So again, there is no extra free parameters. This is the effective Newton constant. So, given a set of observations, and supposing that, okay, the model at hand is the correct model, we need to find the free parameters of a particular model. The method is likelihood analysis using Markov-Chain Monte Carlo. Likelihood analysis was presented in this school, the statistics tutorial. Now, there are three different data set compilations to use. We used separately to be able to understand which dataset contributes to which effect. We use supernovae type iota alpha. We use cosmic chronometers, baryonic acoustic oscillations, and redshift space distortion. Each that's the compilation has somewhat different parameters. Okay, after this step, the second and more interesting step is to decide which of the considered models is preferred by the data. There are many criteria to do this selection. Some of them, if applied together, give not inconsistent results with each other. So we need to employ a lot of criteria to have a, let's say, criteria-independent accession of models. The quantity delta IC, where IC is the value of the information criterion for a particular model, is to be used for us to assign a degree of certainty or degree of belief or whatever for each model. Now the results. This is a particular result for the cosmic chronometers plus supernovae plus Bauer's dataset. With red is the contours from FQ model, and with blue from the control-1. We observe that the models are have similar values to all free parameters, except omega matter, in which FQ model is has some a little larger omega matter. Now, model selection criteria, and this is the, let's say, interesting or not obvious result. For the first data set, lambda DM seems to be performed better than FQ. However, the two models are statistically compatible because delta IC is in all cases less than 2, Jeffrey's scale and stuff like this. Also, in the third data compilation, where we use redshift space distortions. However, for Bauer's dataset, lambda CDM is worse than FQ. So this result, it was problematic for me, along with the team, my supervisor. We delayed to publish this. We think it a lot. We do almost everything. However, the result was persistent. So I don't know. I am close to be persuaded that this is a correct result. This is the value of the parameters. Note that the Hubble tension seems to be not be lived within the model. However, to do a proper assessment of the Hubble constant tension, we need to fit the model to the CMB and compare CMB fitting with direct measurement. Okay. So, to sum up, the exponential FQ model seems to be better in a particular case than lambda CDM. To the best of my knowledge, this is the case for 2 or 3 other models in the literature. However, other datasets show the lambda CDM to be better. However, it is still compatible with FQ. In general, FQ gravity could provide good models, that is, in a close relation with observations. And this model should be studied more. As an extra step, this question remains, namely, could we say that this FQ cosmology is better than SDM? We need to do exhaustive fittings to study more the properties of FQ gravity, and finally to do an e-body simulation. Okay, that's all. Thank you very much.
Thank you for the talk. We have time for questions.
Yes, it seems so. Okay, this is a good question. If I understand correctly, you say that if you decide for a different functional form of FQ, you will have different results. That's right. That's right. This is a fundamental limitation of the approach. You have to put by hand a particular model, particular fractional form of Q or T or R. For example, a Starobinsky model was just a f of R function, let's say. So the idea is to try models that seems to have good behavior observational. There's no fundamental physical principle for choosing the initial, just general assessments for the viability on early or late universe asymptotically. Kostas επίσης. Okay.
I guess this is quite a naive question. I was just wondering about the form of the function you chose, which was like Q times E to the 1 over Q?
Yes, almost this.
Do you take the limit when Q goes to 0, this diverges, right?
Give me a sec.
Or am I wrong?
Think about this expression.
If you take
Yes.
the limit that Q goes to 0, doesn't it diverge?
Yes.
And Q goes like H.
Yes, indeed.
Okay. Seems a bit strange to me, I don't know.
Okay.
Function in the direction diverges then, right?
Okay. Q is related with Hubble rate. Hubble rate, if Hubble rate is 0, then this means that we have a stable universe. No acceleration. What?
Or an inflection point.
Or sorry, again.
An inflection point where the, you know, wait, it's the square Hubble rate, right? Or is it
the square Hubble rate, as you see?
Then you have, so divergence in the pattern.
The divergence should happen whenever H goes 0, but this needs a stable universe, let's say. As a starting point, one should have two-body solutions for the theory and try to see which new terms will appear in Newtonian dynamics. If appear, what can be done, how to parameterize this to run a simulation. Given an FQ model, this particular one or any other, and then if this approach proves to be fruitful, he can add different FQ models. Okay, Kostas.
Then our next speaker is Niki Drepanou. She will talk about Kaniadakis holographic dimension.
Yes. Okay. First of all, I want to thank the organizers for this perfect summer school, and they give me the opportunity to talk about the work of mine and my collaborators, Andreas Limperis, Manos Saridakis, and Karolai Yasmakanova. Let me introduce you to this work. We occur an alternative explanation of dark energy origin through holographic principle. We use UV and IR cutoffs in order to extract the holographic dark energy. Actually, holographic dark energy is a connection between entropy of a system and its geometrical quantities, for example, its radius. Now we generalized. We can use modified holographic models, which are obtained using generalized entropies. This one. Nope. It's not.
Amen. Can you put it back on the presentation?
No.
Thank you.
Okay. Thank you. Thank you very much. Okay. An interesting generalized entropy is Kaniadakis entropy, which is a generalization of the usual Boltzmann-Gibbs entropy. As a result of a coherent and self-consistent relativistic theory. Kaniadakis entropy is a one-parameter generalization of Boltzmann-Gibbs entropy through this equation. This one. K is a dimensionless parameter of the model, and S, B8, is the Bekenstein-Hawking entropy. Indeed, if K is going to 0, this equation obtains the equation of Bekenstein-Hawking entropy. Okay, if K is very small, smaller than 1, we can use the Taylor expansion of the previous equation. In this way, we obtain the holographic dark energy density from this equation. C and C delta is constant, is parameters of the model, and P is Planck mass, and L is the length of our horizon. The equation of motion of our system are the two Friedmann equations, and of course we don't forget the conservation laws for matter density and dark energy density. And now let's talk about the density parameters. We have the matter density parameter and dark energy parameter, and this is a very important step in this work. It's very crucial because we used the future event horizon in our holographic instead of Hubble horizon, because Hubble horizon provides results in other equations which don't recover the usual holographic dark energy, if I'm so simple to say. After some calculations, we can obtain the derivative equation of dark energy density, and of course we define here A and B parameters on there. Okay, here we use the conservation law for dark energy density. It's this one. After calculations, we can extract the equation of W dark energy, the equation of state of dark energy. And now, let's see the cosmological evolution, the physical meaning of these equations. Here we have, oops, I'm sorry. We have the graph of dark energy parameter and matter parameter. As we can see here, this graph is in terms of redshift Z. At the present time, we can see that omega dark energy is equal to 0.7, is in agreement with observational data, and of course, omega matter is equal to 0.3, also in agreement with observational data. So here we have the thermal history of the universe, and this graph tells us the obvious that we live in a dark energy dominated universe. Okay. Now let's talk about the evolution of W dark energy in terms of redshift Z. At present times, we can see that W dark energy is equal to minus of course, okay, don't see that. It's about -1, which is the observational data. So this is okay. And here, let's talk about the acceleration parameter. In terms of redshift Z, here the present time, Q is equal to minus 0.5. It's in agreement with observational data. And here we have, it's a very interesting because it shows that the transition point between the acceleration and acceleration is estimated between 0.6, which is according to observational data. Here we have the effect of Kaniadakis entropic parameter K. Here we have a graph of W dark energy for a fixed value of parameter K and various values of C. Notice that when C decreases, W dark energy takes lower values. Here, looking this graph, we have the evolution of W dark energy for a fixed value of C and various different values of K. And now we can see here that W dark energy decreases in future times. At present times, it remains unaltered, and in future times, W dark energy increases. To sum up, Kaniadakis holographic dark energy is a one-parameter extension of usual holographic dark energy. The analytical expressions for W dark energy, omega dark energy, and Q presents an interesting cosmological behavior. The usual thermal history of the universe is a sequence of matter at dark energy areas. Acceleration transition is about is related with Z equal to 0.6 in agreement with observations. W dark energy can behave as a consequence like phantom-like or experience phantom dividing crossing, as we saw
to the corresponding graph. And in order to our model be a successful dark energy candidate, we have to confront our results with conservational data. Thank you very much. Any questions? Density of dark energy from the entropy. You are talking about the calculations. You mean this? We suppose this is the density of dark energy. We use the Taylor expansion for our Kaniadakis entropy. To do that, we take K be very, very small, smaller than 1. It is something very important, and we cannot avoid it because Kaniadakis entropy itself must be close to Bekenstein-Hawking entropy. And so, as you understand, is something, okay, come on. Okay, it doesn't want to help me. Okay. So it's something inside our entropy. Taylor expansion of the equation we saw, and after calculations, you can reproduce, you can insert this expression. If you want, we can, you can see this paper, or we can talk about the calculations another time, because there are many calculations and we don't have time. Any other? Mm-hmm. It's the same answer. I mean, we just make a hypothesis. We take an equation and expression by hand in order to have a result to fit better to our observations. It's something. There is no rules or something to enforce us to do that, but we just make an effort to plot our data. I'm sorry. Yes? You mean what I... Oh. This one? The next. Okay. So, you mean this point?
No. I guess two slides back.
Okay.
In the starting slide.
Previous? Okay.
You talk about modified holographic model.
Yes.
Does it just mean that there is the entropy with the motion, right?
Mm-hmm. Yeah.
Is there any other modification or just the formula for the entropy?
The formula.
Then you make a
Yes. Uh-huh.
Thank you very much.
Thank you.
Tomorrow, and now let's see
Yes.